Imagine you have malware on your computer, not the catastrophic kind that locks your files and demands payment, the patient kind, the kind that sits quietly in your user session, waiting, collecting. And what it's collecting isn't your documents or your saved passwords. It's something more comprehensive than either of those. It's a searchable, time-stamped record of every significant thing that appeared on your screen. Conversations, financial transactions, login sequences, internal systems, confidential documents, everything that your PC's AI feature has been quietly photographing, classifying, and indexing so that you could search it later. The attacker didn't need to find your files. You assembled the archive for them. This is the security question sitting at the center of Windows Recall, 1 year after Microsoft relaunched the feature with a rebuilt architecture explicitly designed to prevent this scenario. And the uncomfortable part of the story is not that Microsoft did nothing, it's that a credible security researcher says the thing Microsoft was most determined to prevent is still happening, and that Microsoft itself reviewed the finding and concluded it is, by design, not a vulnerability. That disagreement is where this documentary begins. Windows Recall is Microsoft's photographic memory feature for Windows 11. It is available only on compatible Copilot Plus PCs, a hardware class that requires specific AI-capable processors and minimum specifications. Recall is not enabled silently on ordinary computers. Users on supported hardware must explicitly choose to turn on snapshot saving, and enabling it requires Windows Hello Biometric Authentication, a fingerprint or face scan. When Recall is active and saving, it periodically captures screenshots as the screen content changes. Those screenshots are analyzed locally on the device, with optical character recognition extracting text from images. The results are stored in a local database, allowing users to later search their own visual history using plain language queries. Ask Recall to find the presentation you were reviewing last Tuesday, or the website you visited that had the blue chart with quarterly numbers, and it searches the local record to surface matching snapshots. That description reveals the security tension immediately. Every security problem that Recall creates is a direct consequence of what makes it useful. A feature that remembers everything you did creates a record of everything you did. The more comprehensive and searchable that record becomes, the more valuable it is to whoever can access it, including someone who shouldn't be able to. Consider for a moment what actually appears on a screen over the course of a working day. Passwords typed into login fields and briefly visible. Authentication codes displayed in apps before you manually type them somewhere else. Private messages in apps you treat as secure. Internal company documents with client names and financial figures. Medical information, legal correspondence, bank transactions. Credentials for systems your employer doesn't know you access from the same device. Recall doesn't necessarily capture all of these. Microsoft built filtering into the feature. Private browsing sessions in major browsers are excluded. The system filters certain categories of potentially sensitive content, including what it recognizes as password fields and payment card information. Users can manually exclude specific apps and websites from being captured. The feature tries to avoid indexing the most obvious sensitive material, but filtering operates on recognizable patterns. It works well when sensitive information looks like sensitive information, a clearly labeled password field, a website flagged as sensitive. It works less well when sensitive information appears in an unexpected context. A screenshot of a chat application where someone typed credentials in a conversation message, a document where financial information appears in a table formatted differently from what the filter expects, a custom internal application that the classification system has never seen before. The archive's value to an attacker is a function of what was captured, not what was supposed to be captured. And the gap between those two things is exactly where the risk lives. Microsoft spent 2024 redesigning Recall's security architecture from the ground up after the original version was pulled from preview. The criticism that forced that withdrawal was severe. The initial implementation stored snapshot data in an unencrypted local database, accessible to any user-level process that could navigate to the right directory. Security researcher Alexander Hagena demonstrated this by releasing a tool that could dump the entire archive in seconds. It required no special privileges. The rebuilt architecture that Microsoft relaunched in April 2025 is substantially more sophisticated. The snapshot data lives inside a virtualization-based security enclave, a protected execution environment backed by the TPM hardware chip, and Windows hypervisor. Encryption uses AES 256 GCM. Keys are tied to the user's biometric identity through Windows Hello Enhanced Sign-In Security. Decryption is described as happening just in time. The data is only decrypted when the authenticated user actively queries it, not stored in accessible plaintext. On paper, this architecture answers the criticisms of the original design. The encrypted enclave protects data at rest. Biometric authentication controls who can decrypt it. A timeout limits how long the decrypted state persists. Anti-hammering protections limit how rapidly queries can be made. Microsoft said explicitly that this architecture is intended to restrict attempts by malware to ride along with a user's authenticated session. Hagina, the same researcher whose 2024 work forced the original redesign, reviewed the new architecture. His conclusions were specific. He described the VBS enclave as rock solid. The encryption, he said, is genuinely sound. He was not trying to break the vault. He went looking for what happens after the vault opens. What he found is the center of the current security dispute, and it requires a precise explanation rather than a headline. When a user queries recall, the encrypted data in the VBS enclave is decrypted and rendered for display. That rendering happens through a process called AIXhost.exe. This process sits outside the protected hardware enclave. It has no code integrity enforcement, which means Windows does not verify that the code running in it is the code that should be running in it. It has no app container sandbox for isolation, which means it is not restricted from interacting with other processes running in the same user session. And it does not protect against a same user process injecting code into it. Hagina's Total Recall Reloaded tool targets this boundary. Rather than attacking the enclave's encryption, which he confirmed cannot be broken this way, the tool waits for the user to legitimately authenticate with Windows Hello and open recall normally. At that point, decrypted screenshots and extracted text flow from the enclave into AIXhost.exe for display. The tool captures that plaintext flow while it exists in the unprotected process. The attacker's code never touches the encryption. It captures the data after the legitimate user has already decrypted it. The tool demonstrated complete extraction of everything recall had ever captured, operating as a same user process with no administrator privileges and without any kernel exploits. The question of whether no admin needed is accurate has a specific answer. In Hagina's demonstrated technique, yes. Malware running in the user's own session, without administrator rights, without kernel access, and without breaking Microsoft's encryption, could extract the complete recall archive. Hagina disclosed this to Microsoft's Security Response Center on March 6, 2026, providing full source code and reproduction steps. Microsoft reviewed it for nearly a month and closed the report on April 3rd, stating that the access patterns demonstrated are consistent with intended protections and existing controls and do not represent a bypass of a security boundary or unauthorized access to data. Microsoft's position: the enclave protects the data at rest, and once a legitimate user authenticates, access to decrypted data within the user's session is within the scope of normal user permissions. A same user process accessing data available to the user is not a security boundary violation. Hagina's position: that interpretation leaves the feature's most valuable data exposed to any malware that can execute in the user's context, which is a threat model Windows Recall's marketing material implies is addressed. Independent security researcher Kevin Beaumont separately tested the current recall implementation and reached a similar conclusion, writing that the recall database can simply be read as a user process, that no antivirus or endpoint detection and response software generated alerts during his test, and that the database contains undisclosed fields for tracking user activity beyond what Microsoft publicly documents. This disagreement between Microsoft and independent researchers points to the real security issue, one that runs deeper than the specific technique Hagina demonstrated. Traditional malware targeting a compromised Windows session typically hunts for defined artifacts: browser cookies and saved session tokens, credential databases, stored passwords, application data, document files. Each of these targets is specific and finite. The attacker knows what they're looking for and where to find it. Recall creates a different category of target. Instead of a defined artifact, it creates a contextual archive. The archive contains visual records of what the user was doing at specific points in time. Not just what files they had, but what they were looking at, reading, typing into, and interacting with in temporal sequence. For an attacker conducting targeted surveillance rather than opportunistic credential theft, the difference between those two target categories is significant. A credential database contains the credentials someone stored. A visual history archive contains evidence of credentials used, conversations had, systems accessed, and decisions made, across time and context. The protection around that archive depends on whether the user's Windows session has been compromised. If it hasn't, the encryption and Windows Hello requirement create a meaningful barrier. If it has, if malware is already executing in the user's context, then by Microsoft's own interpretation, access to the decrypted data within that session is within the scope of user permissions. The question then becomes, does protecting the encrypted database protect the information when the user's session itself is the threat model? That question doesn't have an obvious answer, and the fact that Microsoft and an independent researcher gave contradictory ones after examining the same implementation is itself meaningful. Step back from the specific exploit technique and look at what Recall's filtering system can and cannot promise. Microsoft's implementation filters out private browsing sessions, recognize sensitive field types, and user-specified apps and websites. These controls are real, and they do reduce what recall captures, but they operate on categories Microsoft has anticipated. The filtering problem is fundamental to screenshot-based features, and Microsoft's own documentation acknowledges it. Website filtering doesn't prevent websites, internet service providers, organizations, or browsers from separately knowing that a website was visited. The filter controls what recall saves, not what the website operator or network sees. These are different things. More broadly, screenshot filtering inherits all the limitations of visual classification. Information in unexpected contexts may not be recognized. Custom internal business applications with layouts the classifier hasn't learned won't trigger sensitive content detection. Content that looks like one thing but contains another, a table whose columns contain credentials formatted as standard text, may pass through undetected. Visual content can be ambiguous in ways that keyword matching isn't. Microsoft's filtering reduces what the archive contains. It does not make the archive safe. Those two statements are compatible, but they are not the same claim. Measured against where recall started, Microsoft has made substantial changes in the year since the original version forced a redesign. Recall is opt-in. Snapshot saving must be explicitly enabled by the user. On managed enterprise devices, recall is disabled by default at the system level unless an administrator configures policies to make it available, and even then, individual users must still opt in to snapshot saving. An administrator cannot enable snapshot saving on behalf of users without their participation. This is a meaningful limit on involuntary exposure. Enterprise management capabilities have expanded. Organizations can use Microsoft Purview data loss prevention policies to restrict sensitive content categories from appearing in recall snapshots across managed devices. Administrators can configure storage limits, retention periods, which apps are included or excluded, and whether recall is available at all. The DLP integration in particular represents a serious enterprise control that didn't exist in the original preview. Users have granular controls, app-level and website-level exclusions, the ability to review and manually delete stored snapshots, and the ability to disable or completely uninstall recall from a supported device. The rebuilt encryption architecture with VBS enclaves and Windows Hello protection is a genuine security upgrade over the original unencrypted database. Hagana is explicit that he is not claiming the encryption is weak. He is claiming that the process handling decrypted data is insufficiently protected after authentication. The question that 1 year of changes doesn't resolve is the one Hagana's research raises. Is the boundary between the encrypted enclave and the rendering process a security gap, or is access within an authenticated user session simply the intended behavior of user-level data? Microsoft says the latter. Hagana says the former and says a fix would require either adding code integrity enforcement to AIXhost.exe as a near-term measure, or rethinking how decrypted data flows after leaving the enclave as a more durable long-term solution. For organizations making deployment decisions, the concern around recall is not primarily about whether every recall installation is compromised. It's about what the archive represents in a worst-case scenario. A managed corporate device used by someone with access to customer records, financial systems, or source code is a device where recall's archive would be extraordinarily valuable to an attacker who has already compromised that user's session. The archive doesn't create the compromise, it increases the value of the compromise. An attacker who has gained user-level access to a machine without recall might extract some credentials and documents. The same access to a machine with recall enabled might extract weeks of contextual visual history of that user's work. For bring-your-own-device situations, the complexity is sharper. The device is personally controlled, meaning the employee makes their own decision about whether to enable recall. Corporate applications, corporate email, and internal systems may appear on that screen regardless of what the employee chooses. The organization's data appears in recall's archive based on what was on the screen, not based on what the employee intended to capture. None of this makes recall inherently incompatible with enterprise environments. It does mean that decisions about recall require deliberate policy rather than default acceptance. Recall is one expression of a principle that will define the next decade of operating system security. The more context an operating system collects about what users do, the more valuable that context becomes to everyone, including attackers. AI-era features need rich local context to work. A system that can search your visual history, anticipate your next task, or continue a workflow you started 2 days ago needs comprehensive records of your activity to do those things. The usefulness and the security exposure are the same data. This creates a new security principle that the industry is still working through. It isn't enough to encrypt stored data. It isn't enough to require authentication before access. The question is, what happens to decrypted data as it moves from protected storage through the rendering, display, and query pathways that make the feature usable? Each transition point in that chain is a potential boundary. Each boundary that lacks enforcement is a potential gap. Microsoft's recall architecture demonstrates genuine engineering sophistication in its VBS enclave design and its Windows Hello integration. The dispute between Microsoft and independent researchers centers on whether the design's sophistication ends too early in the data flow, whether the protected vault is genuinely solid, but the pipe leading out of it is unguarded. Return to the title's claim. 1 year later, Windows Recall still hands malware your entire screen history. No admin needed. The specific technical claim can now be evaluated against verified evidence. Security researcher Alexander Hegena demonstrated, with a proof-of-concept tool and disclosed details, that malware running in the user's session, without administrator privileges, without kernel access, without breaking Microsoft's encryption, can extract the complete recall archive by targeting the unprotected AIX host. XC rendering process. Independent researcher Kevin Beaumont separately confirmed that the recall database is accessible to user-level processes without triggering detection from security software. Microsoft reviewed Hegena's disclosure and declined to classify it as a vulnerability, stating that the access patterns are consistent with intended protections. It did not dispute the technical demonstration. The "no admin needed" element of the title is accurate as applied to the demonstrated technique. The question of whether that technique constitutes a security failure is genuinely disputed between the researcher and the vendor, and the disagreement itself says something important. The boundary between protected and accessible in Recall's architecture falls at a location that is legible to someone with Hegena's expertise and invisible to nearly every other Windows user. 1 year ago, the promise around Recall's rebuilt security model was that Microsoft had addressed the fundamental concerns about an operating system that records everything. The promise was partly kept. The encryption is sound. The enclave design is sophisticated. The opt-in requirement is real. The enterprise controls are meaningful additions. The promise was partly not kept, at least according to the researchers who tested it. The rendering process that handles decrypted data after authentication lacks the protections that would prevent same-user malware from capturing it. The most important thing to take away from this investigation is not that Recall is inherently malicious, or that Microsoft can read your snapshots remotely. It cannot. Or that every Copilot Plus PC is running a continuous screen recorder you didn't ask for. It is not. None of those things are true. The important thing is a principle that applies beyond any single feature. Windows is increasingly building features that remember. The more those features remember, the more useful they become. And the more useful they become, the more valuable their protected data becomes to anyone or anything that can reach it. The real security question isn't whether Windows can remember what you did. It's whether the protections around that memory are stronger than the malware trying to steal it. 1 year after Recall's relaunch, that question is still open.